Okay, so the last lesson that we have for the last chapter of logs is lesson 8, and basically what we're going to be doing is we are going to be graphing logs. So we already did graphing exponential equations, and you were tested on that yesterday. That means Monday's test, you're going to have to graph a log, or we're going to do something with graphing. Before we actually get into the graphing, I want to go through this one question here, which would be a perfect, like, long answer question, this one. So what it says is this point lies on the graph of this log function. So we're going to write the equation of this log function, and we're going to take out the f of x and we're just going to put in a y for now. So let's just write the log function is y is equal to the log c of x. They tell you that this point lies on this graph. So what you could essentially do is you could say, okay, that's an x, that's a y. If you plug that into this equation, what variable would I be solving for? C, right? So if I take that point and I plug that point into this equation, we're actually going to figure out what the base of this log is. So y is -3 is equal to the log base c of x, and x is 1/8. If you write it like this, you could get out of log form to figure out what c is. Viola, how do you get out of log form? We got to turn it into exponential form. So you would say c to the power of -3 is equal to 1/8. You couldn't have done this in Math 10 or 20-1, but now in 30-1, if I say isolate your c, what are you going to multiply this by and then raise this to the power of to get this to be a 1? Because I need to isolate the c. So Adrian, what can I multiply this by? -1/3. Yeah, you multiply it by the reciprocal. So multiply this by -1/3, and then this, put it in a bracket because it's an exponent. What I'm essentially doing is I'm raising this to the power of -1/3, and I'm going to raise this to the power of -1/3. At this point, I now have c isolated. I don't want you to type it into your calculator. So you could, like if this was an exam and you want to double check that you're right, but let's actually do the math. So say to yourself, okay, I want to go from a -1/3 to a +1/3. Sydney, what do I have to do to go from a -1/3 to a +1/3? Say that again. Reciprocate the fraction. So if I reciprocate this, I get an 8. C is equal to 8 to the power of 1/3. Many of you could do this in your head if you convert it to a radical. That would be the third root of 8, and the third root of 8 is 2. So the purpose for giving that point was they want you to plug it in to figure out this remaining variable here, which is c. So now let's rewrite this log function because now I know what the base is. So y is equal to the log base of 2 of x. From here, it says this point is on the graph of this inverse. So they give me another point, but I can't plug that point in unless I know what the graph of this inverse is. So you'd say, okay, well, how do I figure out the inverse of this? So let's write inverse. Logan, how do you get the equation of an inverse? What's the first step? Switch the y and the x. So that would give us x is equal to log base 2 of y. And then from here, step 1 is always switch x and y. Step 2 is isolate y. AJ, how would I isolate y? Exponential form. If you're in log form, get out of it by going to exponential form. So y is equal to 2 to the power of x. So it gives me another point, and it says that point is on this graph. It's on the inverse, the graph of the inverse. So I'm just going to jot that point off to the side. So that point is 4, k. I know that this is a y coordinate, and that's an x. Take this equation, get rid of your y, put in a 4. Or sorry, I wrote that wrong. Get rid of your x, put in a 4, get rid of your y, put in a k, and the question is determine the value of k. So if that's x and that's y, what we would have is k is equal to 2 to the power of 4. 2 to the power of 4 is 16. And that would be your answer. So we haven't really done any questions where we're given points and putting it in, but you would have done that in Math 20-1. Now we're just complicating it by doing inverses, getting out of log form, going to exponential. Let's get into the graphing. Okay, so for graphing, they gave me this graph, but I won't give you a graph on your test, right? If I said graph y is equal to log base 3 of x. So now I'm going to show you the button on your calculator, which I haven't shown you up to this point. Many of you know where it is. What I want to show you first, though, is if you didn't know that there was a button, you would have to enter this by change of base, right? So you would be taking this and you would be saying, well, this is the same thing as y is equal to the log of x over the log of 3. So let's just enter first this method into our calculator in y1, and then I'll show you where the button is. So go to y is equal to, and let's enter it using change of base. So that would be the log of x divided by the log of 3. If you changed your window, just make sure you do a Zoom 6 standard. So that's the graph here. Couple things before we actually enter in y2 the other method. Let's get some points on here. Like, remember the exponential question on your quiz? I said graph it, but make sure you use some good points. So you'd go to second function table, and here's the first point you would choose. So 1, 0. I'm going to write that point off to the side. So 1, 0. The second point I'm going to write is 3, 1. And 9, 2. So those would be the points that you would graph, and then you would connect those points. So 3, 1 and 9, 2. Plot those points. So this would be the 1, 0. This would be 3, 1, and this would be 9, 2. Because what we're going to be doing is we're going to be transforming these points essentially. Even though it has the equation, let's just write it off to the side. This is the graph of y is equal to log base 3 of x. Let's say you wanted to enter this into your calculator not using change of base. So the reason why we teach you change of base is the old calculator, so anybody that has an old calculator won't have this button on your calculator, but where it will be, if you go to y is equal to, I'm going to clear this. I'm going to hit my math button, scroll up, and hit A. This will give you log, and we could enter any base you want, of x. Graph it, and we get that exact same graph. Okay, so you could do either on your test. Like, I'm okay with whichever one. And if I now give you something like log base 3 of, let's say, 81, you could do it by change of base, or now you could just punch that in on your calculator, get the answer. Okay, so now what we're going to do is we're going to do the transformations associated, and we're going to graph each of these. The only work that we're going to really do is going to be for this one, and then you'll see these two, we're just going to move dots around. What parameter do you think this would be? The function is log 3 of x. So I'll do this graph in green. This is my function here, and there's a number in front of the function. Would that be a, b, h, or k? That would be a. If they put a parameter in front of your function, that is the a parameter, and a is equal to 2. The transformation associated with a being equal to 2 is a vertical stretch factor of whatever the a value is, which is 2. The mapping x comma y, remember that your A transformation, what does it affect? It affects y. So the mapping would be x comma A times y. And then our A value is 2. So the mapping would be whatever my point is now becomes x. I'm going to multiply the y coordinates by 2. So the reason why I wrote these 3 points off to the side is let's figure out what the new graph would be with an A value of 2. So x's stay the same, y you multiply by 2. So 2 times 0 stays at 0. This guy would become 3 comma 2, and this would become 9 comma 4. So if you look, this point here is going to be invariant. And watch, we said it was a vertical stretch. This point gets stretched up to here, right? That's a vertical stretch, stretch factor of 2. This blue point gets stretched up vertically to 4, and it goes here. It's ideal if you have different colors. So I'm going to be doing this in green. If you don't have different colors, you'll do like a blue pen and then you'll just highlight it. And if you have different highlighters, you could do that. So now connecting with a nice smooth curve, these points. Would look something like that. Okay, maybe a little nicer than that. And then I'm going to write off to the side the equation of that transform graph, which was 2 times f of x, and f of x, remember, was log base 3 of x. Okay, I'll do my next one in red. So if I said what parameter is this, it's inside the function. Dane, would you say this is a, b, h, or k? This is h. So h is equal to 2. Describing the transformation associated with that, that would be a horizontal translation, 2 units, and then tell me the direction, which is right. Make sure you know the mapping, though we're not actually going to map. We're going to do something faster. X comma y would go to, Kelly, what does my h parameter affect? The x. So it's x plus h, whatever your h is. H is 2. So it's going to be x plus 2, y stay the same. So watch how I want to do this. Instead of mapping each point, go to this point and just 2 to the right. Take this point, 2 to the right. Take this point, 2 to the right. So I'd have a point here, and a point at 11. Now, there's one other thing, and we're going to actually star this one because it's the only one that it's going to occur for, that's going to move 2 to the right. Does anybody know what else would move 2 to the right? The asymptote, yeah. So what I'm just going to show you, and you're going to put the asymptote in. You won't put the, I mean, you could put the initial one in, but watch what happens. So I had this in red. Okay, we know that the initial asymptote is right here. So let's actually just mark that. The equation of the initial asymptote is x is equal to 0. So that green graph has an asymptote of 0. This red graph, though, if I moved all of my points 2 to the right, you also have to move your asymptote. So 1, 2 to the right. Now let's put in the equation of this asymptote. So the equation of my new VA is now x is equal to 2. And the reason why you want to have that on your grid is because now you could draw the picture. Like now you know, like you will know that these 3 dots will be connected, and then it's going to get close to your VA, hug your VA, but never touch or cross your VA. So it would go down like this, arrowhead at the bottom, and then it'll go like that. So that is the graph of y is equal to the log base 3 within my function x minus 2. I'll do the last graph in pink. This is my function. Cole, what would the negative 2 be? What parameter? That's your k value. K is equal to negative 2. Describing the transformation, that is a vertical translation, 2 units. Tell me the direction, which is down. Tell me the mapping if I ask for it. So x comma y would go to, the k value affects your y. And remember, it was y plus k. If your k is negative 2, it's just y minus 2. We're not actually going to map anything because we're going to look at our 3 original points and we're going to transform each of these 2 units down. This guy, 2 units down. This guy, 2 units down. I'm going to put my VA back at 0 because it does. If I take this and I say move this 2 down, that doesn't make sense, right? So I need my VA back at 0, so at least I know how to plot this. So this one, 2 down, would go here. This guy would go here. And this guy would go here. Connect those dots with a smooth curve. And that would be the graph of y is equal to the log base 3 minus 2. So outside of the function, I subtract a 2. Okay, so let's answer a couple questions about these. Do any of the above transformations result in a change in the original domain or range? So let's actually start with the range. Look at all of those graphs. They all have the same range. What is the range of all of these guys? It doesn't matter what transformation you do, what's the range going to be on a log graph? YER. Yes. So though that's no parameter is going to affect our range. There was one parameter that affected the domain. Okay. What was the parameter that affects the domain? Kelly? Yes, the H parameter. So for this last one, the domain, it's only the H parameter. So let's star that. Only the H parameter affects the domain. So essentially, the domain of my red graph was x is greater than 2, right? If my VA is at 2, that's my VA. The domain is x is greater than 2. So I'll write that. The domain is x is greater than 2. The other graphs, if there's no horizontal translations, the other graphs are going to be x is greater than 0 because the VA is always at that, the asymptote is at x is equal to 0. State the equation for each asymptote. This is where it might have caught up on your photocopy. So we just have to say the equation of the green, the equation of this guy, and the equation of the pink. So it's very little that you're going to write. So number 1, which is green, the green graph, the equation of the asymptote, it was x is equal to 0. The red graph was the one with the transformation, and the asymptote was, remember we moved it over 2 units to the right, so it was x is equal to 2. The third graph, which was the pink graph, we didn't move the asymptote at all, so it was x is equal to 0. All right, so that's transformations. Let's see what a test question would look like. So for this next one, if you want to star this one, this would be a perfect, again, long answer question, right? Because there's tons of stuff that I could ask you in this. I would have asked you this, all of this stuff in your quiz for exponential graphs. Now we're just going to do a log graph. So the original graph is y is equal to log base 3 of x. That was what we just did, right? So if I go back here, that original graph up here was y is equal to log base 3 of x. We could get points for the original graph on our calculator, but we're going to actually do this entire question graphing nothing. We're not even going to look at any of these graphs. What it says is take this original graph and have it undergo, transform it to this equation here. So let's write the equation of the transformed graph, which is y is equal to, this is the transformed graph, so log base 3 of 2x plus 6. So the first thing that you'd be asked is describe all the transformations. What's the a, b, the h, and the k? Remember, you always got to factor out that b. So I need you to rewrite this equation with the b factored out. So the equation with the b factored out would be log base 3 of 2 of x plus 3. Just like when we did the transformations unit, remember I said, like, on a test on the diploma, they will never, they'll always give it to you like this, and you'll have to see the b factored out. Because where they're going to get students is everybody's going to say the b value is 2, and everybody's going to be correct. Students that don't factor it out are going to say the h value is -6, and they would be incorrect. So then from here, let's write our parameters. A, I'm not going to bother with. It's a 1. This is my b parameter. So b is equal to 2. The next one is my h parameter. H is equal to -3. There is no k parameter, so they're not moving the graph up or down. If you were to describe each of these, you would just very quickly say, okay, what's the b parameter? That's the horizontal stretch. Stretch factor of the reciprocal of b, which would be 1/2. H is equal to -3 is going to be a horizontal translation. Tell me how many units in what direction? 3 units left. So that's describing all your transformations. Next thing I could ask is, what are the x and y intercepts of this graph algebraically? So not punching anything into your calculator. So let's see how we would do this algebraically. If you are looking for an x-intercept, you always let the other letter equal 0. So let y equal 0. I'm going to rewrite this equation, and I'm going to put a 0 in for y. 0 is equal to log base 3 of 2x plus 6. Now we got to solve for it algebraically. You're in log form. Get yourself to exponential form. 3 to the power of 0 is equal to 2x plus 6. Anything to the power of 0 is 1. Let's isolate our x, so subtract 6 from both sides, and I get -5 is equal to 2x. Divide both sides by x, and I'm going to get x is equal to -5/2. I tend to convert x and y intercepts to decimals because if you are plotting it, you need to know what that decimal is. So this is an x-intercept of -2.5. I would accept that. X-intercept even equals -2.5, like I'd accept that. Or the other thing that I would accept that some of you wrote on your test is what is the x-intercept as an ordered pair. So -2.5, 0. So that's how you'd solve the x-intercept algebraically. The y-intercept, we have to let x equal 0. So if we're solving for y, let x equal 0. So we're going to write that equation, and we're going to put in a 0 for x. So y is equal to log base 3 of 2 times 0 plus 6. Y is equal to log base 3. 2 times 0 is 0 plus 6 is 6. From here, you would be allowed to punch that into your calculator. Remember that there's now two ways you could plug this into your calculator. You could either enter this as change of base, log base 6 over log of 3, or now you could use your button. So let's use it over here. So again, I'll show you both ways and that you get the same answer. Log base 6 divided by log of 3, make sure you close the brackets on your arguments, is going to give us that y-intercept of 1.63. And if I use my math button, go up to your log base, and I want a base of 3 and an argument of 6. And look at that. I would have to specify to what decimal place. So let's say I said to the nearest hundredth. So 1.63, y-intercept is equal to 1.63. Or you could say the ordered pair, when x is 0, y is 1.63. So x and y intercepts algebraically. What's the range of my log graph without even looking at it? YER. I'm now going to show you a trick that you're going to do every single time I give you a log, and this is going to show you the domain and the asymptote. I want you to write the equation of the transformed graph. Y is equal to log base 3 of 2x plus 6. And we're going to be doing this over and over again this lesson and then next week. When I first introduced logs to you, I gave you a restriction on the argument. I don't know if you remember what that restriction is. Does anybody remember what the restriction was? So the restriction on a log is the argument must always be greater than 0. It could never be 0 and it could never be negative. So let's actually just write that down. There's always going to be a restriction on the argument. An argument must always be greater than 0. So if I ever ask you for a domain or for an asymptote of a log, you're just going to look at the argument. And what you're going to do is you're going to take this argument and you're going to make it greater than 0. From here, you're going to solve for x, and you've got the domain. 2x is greater than negative 6. X is greater than negative 3. That is the domain of this graph. And just to quickly show you, you guys, watch this. If I go back to this page, each of these, so if I just erase this, so you're going to be able to do domains and VAs very quickly. What is the domain of this graph? The argument must always be greater than 0. That is the domain. This graph, what is the domain of this graph? Remember we said it was greater than 2? How did we get that? The argument must always be greater than 0. Solve for x. X is greater than 2. That is the domain. If I said really quickly, what is the domain of this graph? You only give me your argument, and the argument must always be greater than 0. Therefore, the graph must be greater than 0, or the domain must be greater than 0. Once you have the domain of the graph, the asymptote becomes easy. Take out this inequality and put in an equals. So there is, you just have to remember if it's a log graph, it's a vertical asymptote at x, I'm going to change this, is equal to negative 3. So this graph would have a VA at x is equal to negative 3. And then we've answered absolutely anything I could ask you about this log graph. So just to apply this, to see if you understand what we did, let's look at some diploma questions. And none of these we're going to punch in. The equation of the asymptote for the graph of, it's a log graph, and it's asking about an asymptote. So what I always tell students for a log graph, first figure out what the domain is, and then get your asymptote. So whenever you have a log graph, you always take the argument, and the argument must always be greater than 0. Solve for x, and we now have the domain of this graph. So in like 2 seconds, we got the domain. In 2 more seconds, you're going to get the VA. So Viola, there is a VA at, what's the equation of the VA? That's for x, yes. X is equal to 3. You just take your domain, substitute out the inequality for an equals because it's got to be an equation, and your answer would be C. Yes. Yes, in this one you could have. You could have said to yourself the H value is 3, this graph, the VA would go 3 to the right. Yes. But then this one, right? Let's just look at, I mean, we could figure out the H value by factoring out the 3. Like we could do that. But really, a quicker way is I would just always take this. The argument must always be greater than 0. So 3x plus 12 must be greater than 0. 3x is greater than negative 12. X is greater than negative 4. That is the domain. If I said, what's the VA? Dane, what's the VA of this graph? VA at, what's the equation, sorry? X is equal to negative 4. But they were asking about the domain, so that was the answer, which is A. Viola, to go back to what you were saying, if I factored out that 3, I would have x plus 4, and yes, the h value here is negative 4, so the VA is going to move 4 to the left. That's how you could do that. But I just find this one so much faster to do. I always just argument greater than 0, solve. This question. Again, it looks really scary, but we're going to do the question so quickly if you know where VAs and HAs are. They give you 2 graphs. This is a log graph. What is this graph? If it's not a log, this graph is, yeah, this is an exponential function, a to the power of. This is an exponential graph. This is a log graph. So what it says is a student sketched these graphs. She also drew the asymptotes. So this question is just about asymptotes. So let's do the log graph first, because that's the one we're used to right now. This is the one fresh in our head. If I said, what's the asymptote of this graph? Quickly find the asymptote of this graph. If it's a log graph, the argument must always be greater than 0. X is greater than negative 3. That's the domain of this graph. But they want the asymptote. So we have to say, you have to remember that a log graph, it's a VA. So VA at X is equal to negative 3. What it says she did is it said she drew the asymptotes of the 2 graphs using dotted lines. So let's put this asymptote in. Go to negative 3. And if you have your ruler, draw yourself an asymptote. And the equation of that asymptote would be x is equal to negative 3. Then there's an exponential graph. You were quizzed on this yesterday. Where is the asymptote just by looking at it on an exponential graph? What parameter was it? It was the k value. So we're going to star this one if you forget it. So this is an exponential graph. The k value is equal to 5. On exponentials, were they horizontal or vertical asymptotes? What were they called? They were horizontal. Therefore, there's a horizontal asymptote at, what's the equation of the HA? y is equal to 5. You take that k value and just swap in a y is equal to 5. Can you now draw a dotted line at the equation y is equal to 5? Or put that line in. So y is equal to 5, 1, 2, and here would be my HA. The question is, the intersection of the 2 points of the dotted lines is that guy right there. Brandon, what's that answer? Yes, -3, 5. So for the exam next week and for your quiz on Monday, I'm not going to test you on Monday on exponential graphs. That's going to be retested on the exam, right? So, but these two, you just have to know where those asymptotes are. So make sure if you're doing study sheets that like this would be on a study sheet. If it's a log graph, the asymptote is when you find the domain of the argument. If it's an exponential graph, just get that k value. There's your asymptote right there. Remember that this one is your VA, this one is your HA. So students will sometimes forget those two, and then you get the wrong answer if you forget. Hey, let's do this last diploma one, and then we'll finish off transformations. This graph is reflected in the line y is equal to x. So this is reflected in the line y is equal to x. What does that mean? If something's reflected in the line y is equal to x, yes, what does it mean? It's an inverse. Yeah. Whenever you see this, inverse. Or remember if you saw this, f inverse of x, that's going to be inverse. So if I said what's the inverse, you'd say, okay, step 1 is interchange my x and y. Step 2 is to isolate y. The only way that you could isolate y, if it is in exponential form and it's an exponent, is by converting it to what? Log form. So I've never got you to make a log when my exponent was a binomial, but it's the same process. So if I said log, what would my base be? The base of your exponential graph is going to be the base of your log graph. The answer becomes my argument, and that is equal to y plus 2. From here, you've got to subtract y from both sides, or sorry, subtract 2 from both sides, and you would get y is equal to the log of 3 of x minus 2. The answer is A. Do you know what a lot of students would choose? What's the main distractor that students would choose as the incorrect answer? C. They would choose this guy. If you look here, y is basically replaced with y plus 2. So you say, well, what parameter would that be? That would be a k parameter. The k value is -2. When I bring it over here, that's my k parameter of -2. If you chose this, you all of a sudden made it into an h parameter and you put it inside the function. Right now, this is outside the function. It has to stay outside the function. Okay, last thing we're going to do is I need you to know the difference between, so right down here, y is equal to log base 3 of x. So that's the one we did, right? It was this guy right here. What would the transformation be if I took this base and I reciprocated it? So y is equal to log of 1/3 x. So the last thing we have to know is what happens when this gets reciprocated. Do you want to guess? No, close. Let's graph it. So on your calculators, Go to y is equal to, we already got this guy in. Keep that in y1. In y2, let's go, let's do our button. So math, log base, change that 3 to a 1/3, and put in your argument of x. What transformation was this? It's a not the y-axis. It's a reflection in the x-axis. This would be a vertical translation. So this is going to be a vertical translation. We cut the x-axis. So the transformation is a vertical not vertical translation, vertical reflection. And then you always have to tell me the axes you cut. So you'd say in or about the x-axis. We know that this original graph, remember we had this was a really nice point, 2, 1 was a nice point, and this was a nice point. Here's how you're going to do it really quickly. This point, if this is my mirror line, instead of going up 1, it's going to go down 1. Right? So on my new graph, it go down to here. This is, remember, my mirror line, the x-axis. So this point went up to, the transformed point would go down to. This x-intercepts are always invariant. Remember when you cut the x-axis in a reflection, what axes you cut, those are going to be the invariant points. So the new graph of the reflection would look like this. So we are not going to do these last two, but what would be the vertical reflection of y is equal to log base 10 of x? It would be what? That's right. It would be this guy right here. So log base 10 of x, if I said what's the equation of that after it undergoes a vertical reflection, you would say, oh, that 10, we have to reciprocate, becomes 1/10. The other way I could ask it is I could say y is equal to log base 4, or sorry, 1/4. Let's actually change that so it looks like a base. So y is equal to log 1/4 of x. What would this become? Dane, what would this guy be after it undergoes a vertical reflection about the x-axis? Yeah. So vertical reflections, all we need to know is that we reciprocate that base. All of these domains are going to be what? All of these guys, the argument must be greater than 0. That's how you get the domain of any graph. The argument must be greater than 0. So x is greater than 0 is the domain of all of these graphs. The ranges for these graphs, Kiernan, would be what? YER. The x-intercept of all of these graphs are invariant points if they're vertical reflections of one another because they cut the x-axis. So the x-intercepts are going to be invariant. So I'm going to write IPs. And the x-intercepts are, remember, 1, 0. What is the equation of the vertical asymptote? If the domain is x is greater than 0, the VA is x is equal to 0. That would be your VA. Again, what do you notice between log base 3, log base 1/3, vertical reflections? These points here, these are just the notes that we just went over several times, right? Domain for the argument must always be greater than 0. Here the argument is just x. Our range is YER. These graphs would have an x-intercept at 1, 0, and it will always have a certain shape. Now, um, the last thing that we want to write down is this one here is the shape of your graph if b is greater than 1, right? So this would be the shape of the graph, the one we did, y is equal to log of base 3x. As soon as b becomes a fraction, so less than 1, greater than 0, basically what we're doing is we're reciprocating this, right? As soon as it becomes a fraction, the graph is going to change to this because it underwent the vertical reflection. So this guy would be y is equal to log of 1/3 x. I could make this any number greater than 1. So I could put a 2 here and a 1/2. I could put a 4 here and a quarter. I could put a 5 and 1/5. It's just these are the shapes you have to recognize. All right, I've got 2 more diploma questions, and then I'm going to give you your homework. I like this question because there's a really good distractor, and it could be done in 2 ways. So half of you might do this one way, half of you might do this another way. Just to quickly go back again to the exponent laws in grade 10, if I gave you this, you would say bases are the same, you add the exponents, right? The answer if you add an A and an A is 2A. So with this, bases are the same, they're being multiplied, so that's product law. We would add our exponents. So that would be 3 log of x plus log of x. So no matter which way you're going to solve it, everybody should have that first. Some of you might say log of x plus log of x is 2 log of x, because these are like terms, just like an A and an A would be like terms. They could be combined to 2 log of x. You would then look and you would say your answer is not there. So what can I do to this to change it? And it would be put your coefficient on the argument, and that would give you A as an answer. Okay, so that's one way, that a student might do this. The other way is if you see log of x plus log of x, what law could you apply here? The product law. So the product law would be, so jot this one down as well, because you might see this one even more. That would be log of, the product law says we have to multiply the arguments. So that would be x times x. That would be 3 log x times x is x squared, which gives us A no matter which way you do it. Do you know what the distractor would be? It would actually be C, because students would say, well, is that not going to be the same thing as this? And the answer is no. If the um, exponent is on the outside of the bracket, it's the bracket twice, right? So C would be, what this guy would be 3 log of x times log of x. If you wrote that bracket twice, there is no law for multiplying logs. There's only laws for adding and subtracting logs, right? So that's, C would have been the main distractor for this one. Okay, this one I find pretty complex, but they want us to write this in exponential form. You always have to isolate your log. So we got to get somehow this log by itself. So first thing you should see is get rid of that 5. What we would then have is m log p argument n is equal to q minus 5. The log is technically not isolated yet because there's an m in front of it. So before I taught you the log laws, a lot of you would want to be like, oh, let's divide this side by m, let's divide this side by m, and that might work. But if I like look up here, they're all having this q minus 5, right? So they're not like dividing this side by m, dividing this side by m, how else could I get rid of that m? Do you know where I could put it, Sydney? That's right. Put it on the argument. See if you could get the answer now. Log base p n to the power of m is equal to q minus 5. Get yourself into exponential form. P to this power. The power is a binomial. Put the binomial in a bracket. So p to the power of q minus 5 is equal to n to the power of m. And I believe that answer is there. Q or B. Here's your homework. So 1AB, 6, 7, 8, 12, 13, and 15. So get started on that first. And then you could do the final review that I gave you.